So, okay, it was a little bit, yesterday may have been a little bit confusing because it was a little bit confused. So I don't exactly know how to where to go from here, but we'll improvise and we'll see. So, okay, so yesterday what I did, I think, what I tried to do is first give you a very rough idea of why you can hope to get the following evolution, which is a weak evolution. So I rewrite what I wrote yesterday. So there exists, so assuming that, I'm not going to repeat that, omega is smooth enough, that the boundary loads are smooth enough, there exists a function phi of t, and there exists a crack gamma of t, which grows with t, such that for all t in your interval of study, so two items. One, the integral over omega, or three items, I should say. The integral of w of grad phi of t dx is less than the integral over omega of w of grad psi dx plus k h1, because we're in 2 dimensions, but the theorem is also applicable in 3D, and it would be h2 of gamma minus s, s phi s psi minus gamma of t for all psi which are kinematically admissible. So let me write what it means for all psi which are in SBV. And here you have to be careful that it's not really true. There is a little mathematical complication here of omega with values in R2 and which are such that psi equal g of t on the boundary. And what? Okay, so why am I writing it in quotes? It's because psi could really jump on the boundary. So it could be that actually there's a jump. Okay. So the easiest, the simplest way to deal with this is to assume that psi is defined everywhere, and that I remind you that g of t already, I had done that for g of t. I defined g of t at every point x of the plane, and here I would define psi everywhere on the plane, and I would force it to be equal to g of t outside omega bar. So you have your domain omega, you take its closure so that the boundary is included. Outside you put psi equal g of t everywhere outside omega bar. And that way, since psi can jump, if it wants to jump on the boundary, it will jump on the boundary. Okay? Of course, okay, so to be consistent here, I have to backtrack a little bit. I should really have let the crack go to the boundary, which I did in the note that I gave you. Now, from a physical standpoint, it is not clear. The boundary should be somewhat special because it's not clear that the fracture toughness on the boundary should be the same as the fracture toughness inside. So you could have a K which is different on the boundary from what it is inside. Here I'm kind of assuming that a crack on the boundary, a crack at the interface is the same thing. In reality, it shouldn't be. In reality, it shouldn't be the same thing. Similarly, I had misunderstood Francesco's question, which kind of flew by yesterday in a storm of questions. So, okay. So here I chose Griffith's energy. So an energy which is proportional to the crack length. So there's one thing which fits squarely within this framework as well, which would be an energy which depends, which integrates the fact that there might be anisotropy. Here there's nothing isotropic about this function. Why should there be isotropy in the surface energy? If you have an anisotropic material, you expect the fracture toughness to be maybe anisotropic as well. And so you could put here, instead of that, something a little bit more complicated, which I'll just write here, which is an integral over the jump set of psi of a function k of the normal to the jump set, k of nu, dh1, with certain properties of k with respect to nu, for example, convexity. However, you have to be careful that if you start putting something else than the dependence in nu, for example, the dependence in the size of the jump, then you get into a different model. So it's okay to have a k which essentially looks like a norm, so which depends on nu. It's not okay to put a k which depends on the size of the jump, because then you're going into a different kind of surface energy, because it tells you the amount of energy you spend by opening something depends on the size of your opening. And then you get into what's called cohesive models. And and I don't want to talk about this. So let me tell you the reason why, and then, just for your... this is kind of a zoology of this kind of methods. The reason is that if you do that, as you saw, the first issue that we had to deal with was existence. We discretized time, and at each time we had to show existence of this minimizing problem suitably discretized. So you replace gamma of t by gamma I minus 1 and g of t by gi. When you do that, and you have the kind of energy that a kind of energy where k would depend also on the display, on the jump. So that's called a cohesive model. So you have then something happens which doesn't happen in Griffiths, which is that this problem, or the discretized version of that problem, doesn't have a solution. There's no global minimum. In order to attain a global minimum, you have to, so depending where you come from and what your language is, you have to, but I like that word, you have to relax the problem. And that's something that hasn't been broached at all in this meeting, but there's a huge class of variational problems for which, if you're looking for a minimizer, of your energy, you don't have a minimizer. Why? Because, for example, your energy prefers to create objects at a different scale. So in the language of mechanics, you would say that there's creation of microstructure. Here, it's exactly what would happen with cohesive energy. It would tend to create something which looks like a microstructure. So it's not a microstructure because there's no heterogeneity in here, except, I mean, you could put an X here if you wanted to, but it's not on that scale that it would happen. But there would be a relaxation process. And okay, so just so that you've heard of it, if you try to do this with cohesive models, so you put a dependence in the jump set of U, what you end up with is a problem where at each discretized time, you don't have a solution, you have to relax, and the kind of model that you end up with has a weird property. So you get as energy here something which is what you started with, but it poisons, it infects your bulk energy. And so essentially you start with a problem which is a problem of elastic fracture, and you end up with a problem which is pure plasticity. So I'm not telling you why, but just be careful. So before you start, if you were going to try some experiments, let's say some numerical experiment, and you said, okay, I'm going to put also dependence on the displace on the jump here, you could run into huge problems. Close the parenthesis, and so that was the first criterion. The second, and I'm going to come back to this just for a moment, is that S of f of t of phi of t, the jump, the points where phi of t will jump, is included in the crack set. And the third one, which I won't repeat because it's the balance of energy. Okay, so let me come back to this 1 minute. This theorem is a bit weird, this result is a bit weird, because it tells you there exists a phi of t and a gamma of t. There exists a crack, but it doesn't tell you exactly what that crack is. You see, that item here, item 2, only tells you that wherever your kinematic variable jumps should be in the crack at that time. So, for example, so this has to be complemented by a remark. You can choose gamma of t to be such that gamma of t is the union over all prior times up to t of the jump of the phi of s. So this is a problem which is typical of non-uniqueness. So it's fairly, let's say you're dealing with a strictly convex function here, W, which, as Professor Del Piero mentioned 2 days ago, is not compatible with frame indifference for reasons that you can find in any book on elasticity. Then for a given gamma of t, you have uniqueness in you have uniqueness of that minimizer phi of t. But it doesn't mean that you have uniqueness of the pair phi of t, gamma of t. In order to achieve this kind of result, which is saying essentially that gamma of t can be seen as a union of the points where in the past any of the displacement field or transformation field has jumped. That result requires first to prove this theorem with a gamma of t which doesn't have to be that, and then to show that you can choose a different gamma of t, which is this one, which in a way, in a sense, is a minimal crack that you can generate with those phi of t. But it doesn't tell you it's unique. There's no, so that's one of the other remarks, no uniqueness. Now let me also emphasize that this no uniqueness is generic in all mechanics problems which are not convex. It is only in a strictly convex case that you can prove uniqueness of solution. And you all know, I mean, and so maybe I'll show you a movie later, and you'll see that there's an evolution, and you'll see that the crack starts, it's completely symmetric, and I don't know if I can find it here. So, but anyways, I'll tell you more. It doesn't matter. Pictures are distracting. I don't like pictures. So you look at a perfectly symmetric thing, and you see with a loading which is symmetric, and then you see a crack starting, and the crack is asymmetric. And so you get this reaction from a lot of people in the mechanics community. How can it be? Everything is, yes? Even is symmetric. There's no crack at the beginning. Okay, maybe I should try and find this movie. Okay, it doesn't matter. I mean, right? It doesn't matter. Does it matter? Yeah, it matters. Okay, so I won't find the movie. No, so it's a good thing to show a picture. It's a good thing to is that what you're saying? So I should show the picture. Yes, we are going. Okay. GAF. I will show you other pictures later, of course, after I talk a little bit about the numerics. So let me see if I can find this thing. I think I can. So no. So this is maybe good. Yeah, this one probably has it somewhere. Yeah, actually that's the one I had already. Sorry, no. So, yeah. Yes. Sorry, after a while you end up having so many files that nope. So that I will find it. Pizza. No. Yes, that will be here. Can you turn the... Oh, it was here. Nope. Wait, pictures.
Otherwise you are upset without Victor.
Yeah, no, I will find it. I will find.
If you start quarreling with a computer, it could be even worse.
It could be worse, you're right, but I will find it because I'm stubborn. I had to learn to be stubborn here during this week. I wasn't stubborn before. Okay, so it should work. Okay, so here is the thing. And I'll tell you in the rest of my time, oops, so I'll tell you in the rest of my time, I'll tell you in the rest of my time how we do this computation. But essentially, you have a square. In that square is elastic. It's clamped to a rigid shaft. It's a 2D problem, and you pull on it up there with an increasing displacement. You have no crack to start with, but it's a global minimization problem, and you will get a crack eventually. This is completely symmetric. There's nothing more symmetric than this. And here is the solution that you get. So at the beginning it's elastic, and then suddenly, I'll explain the colors in a little bit later, suddenly you have a crack which is symmetric for now, but then you'll see that it does something asymmetric. And then it keeps on and it breaks. So, okay, I don't want to discuss this right now. Just to tell you...
Victor should say that your code
is bad. Yes, and it's not. Because you all know something which is completely asymmetric thank you, in elasticity, with a completely symmetric load, and it's called buckling. Okay? It doesn't buckle in every direction, because I don't know how you would do that at the same time. So buckling is asymmetric. It's a perfectly symmetric problem with a perfectly symmetric load.
So Victor would be right, because in your case there are small perturbations leading towards one of the...
Okay, so that's because you need a small perturbation to do it, but in fact you don't need one. All right, so that's very important, no uniqueness. I think buckling is a buzzword. Once you know buckling, suddenly you realize that symmetry is not something which has to be preserved by the solution of a variational problem. Okay, so here, so that's what I wanted to tell you about this problem, about this. So what I would like to address today. Okay, so no, maybe the second thing is then I did the example to show you. So let me be clear on what I did yesterday. Okay, I took a bar. That's a matter of length L, and I pulled on it with a force sigma. And I looked at whether or not global minimality, because we saw that the day before yesterday that when you pull and you look for a global minimizer, the best thing you can do is to cut, to send it to minus infinity. There's no minimizer. But I pulled on it and I asked myself, is it possible to get to satisfy the first thing that I had written, which is unilateral stationarity and or local minimality? And the answer was yes. The elastic solution is always locally stable or locally minimizing, and even unilaterally stationary, if you want. So from the standpoint, so what it says, and since we saw that modulo smoothness, our formulation was at the beginning, before I started weakening it with this kind of functional formulation, was equivalent to Griffiths. Griffiths is telling you, and our formulation is with unilateral stationarity is telling you, and it's the only one. It's the only one. It is the only one. So it tells you that in a problem with, in this very simple problem of 1D traction, if you do Griffiths, you never generate, you don't see any fracture. Okay? As I said, I really think you should try to do it. I'm not going to do it. It's exactly the same thing. Well, not quite, not completely, but nearly. If you do it with, instead of a sigma here, which is a load, an epsilon here, or an epsilon L, which for a given epsilon, a displacement, you will find a completely different picture. The computations will be the same. There'll still be the fact that EU prime equals sigma, some sigma. The difference is that sigma is not imposed. It's just a stress inside if the bar is completely elastic, you compute the sigma as a function of the displacement that you apply at the end. That's strength of material first course, first week. But you can play with that sigma. In particular, you can have that sigma equal to 0. And then you can have jumps. That's not contradictory. And then you find that there is a globally minimizing solution. So the result is in the notes. There is a globally minimizing solution when you pull with a displacement load. There are also the fact that any solution where you break with one break, 2 breaks, 3 breaks, they're all locally minimizing. All locally minimizing. Of course, it's a stupid example, but okay. And then there's another example, there's another example which is worked out in the notes where you see the opposite. There's uniqueness. It's a tearing. Where there's uniqueness, so the solution that you describe is satisfies everything: local, unilateral stationarity, local minimality, and so on, and global minimality. So it's very situation dependent what you get. Okay. So now let me go on to. So let me remind you of the discretized thing once again. Maybe I'm repeating myself a lot, but it's okay. So I have Ti minus 1, and I have Ti. And here I have Gi minus 1, and I have Gi. And I want to compute, so I know Phi minus 1, I know gamma I minus 1, and I want to compute phi and gamma I, and so what I want to do is minimize integral over omega of W of grad psi plus HK H1 of S psi minus gamma I minus 1 over all psi which are equal to Gi on the boundary, and then I will get, if I can do that, I'll get a phi, and then the phi will have a jump, which is S of phi, will be the jump, and then I'll call gamma I minus 1, union S of phi. So now here, for those of you that are interested in computations, and I hope it's who has absolutely no interest in computations. You don't be afraid to say who never wants to use a computer in their life. Yeah, you don't. Truesdell is dead, but there might be another one in being here. A Truesdello, maybe. So if you want to do computation, how are you going to do this? So this is really an issue because you see, so you could say because the psi can jump anywhere it wants. So if you're a finite element freak, you could say, yes, what I'm going to do is I'm going to take a triangulation of my domain, and then I'm going to use non-conformal elements or elements that can be discontinuous. So there's a whole literature which is based on what's called XFM, I don't know how you call it exactly, extended finite element methods. The problem with this kind of things is that they're, there's a huge literature on this, and not only, people use that in fracture, whatever method they want to use for fracture. It has a lot of problems. One of them is that it's very mesh dependent. The second one is that it constrains the topology of the mesh to the topology of your fracture to the topology of your mesh. It tends to create only connected cracks, things like that. So, maybe it can be used. There are a few. There is one person here in this country who's a strong proponent of these methods and who's done beautiful work on this. And his name is Negri. I don't remember where he is. So if you want to, so with XFM in this context, the relevant work to look at is the work of Negri. Matteo, I believe, Negri, and he has. So if you go to Web of Science or MathSciNet or Google, you'll find his articles. But this is not our viewpoint. So our viewpoint is once again based on the literature on image segmentation and on the work of De Giorgi and his school. So not so much the work of, the work on De Giorgi first. So the idea is let's go at the first time step to understand what happens. First time step. So the goal is to minimize integral over omega of W of grad psi plus K H1 of S psi among all psi which are in SBV and which are such that psi equals G0 on d omega. So the value of G at time 0. So the idea, the idea is very Italian, in essence. So the idea is to approximate this functional by a sequence of functional with a small parameter, and to use the notion of gamma convergence. So I'm kind of happy that Professor Berdichevsky is not in the audience because he would be jumping up and down for sure. So, because one more mathematical tool. Okay, so you're Italian. So I'll go very fast because I know you've all heard that word before, gamma convergence. So, essentially, you have a sequence of functional f epsilon, which are defined on a Banach space X with value in R. and you want to define its gamma limit. So you'll say that f epsilon gamma converges to f. So now you have to be cautious. Gamma convergence is not something which comes out of nowhere. It's tied to a topology. So it converges for the topology that you put upon X. Okay? So it's if and only if two things. One, for every sequence U epsilon in X, which converges in that topology to a U in X, so it can be, I'm going to write it like this, it converges in that topology, then f of U, so f, which is also a functional from X to R, f of U is less than or equal to the limit in epsilon of f epsilon of U epsilon. Second, for every U in X, there exists a subsequence U epsilon which converges to U in X such that f of U equal the limit of f epsilon of U epsilon, or U tilde epsilon, which can be identically, which can be equivalently replaced by greater than equal to the lim sup. And why is that? That's clear, because the lim, since on the one hand by number one it's less than the lim inf, and then it's greater than the lim sup, the lim inf is equal to the lim sup is equal to the limit, and it's a limit. Okay. Now, the only thing you need, I mean, so that's a completely theoretical definition. There's one thing which I will give you as an exercise, but which is a trivial exercise, okay? Which is a fundamental property of gamma convergence, which is extremely useful and which makes it useful in our context, is the following: that if you're solving this the following problem, inf of f epsilon of U epsilon, if of f epsilon of V, and just to be sure that I don't, just to make things different, I'm going to subtract a linear functional of V, just to mimic something like body forces. I want to do the inf over V in X of f epsilon of V minus L of V. That inf, an inf always exists, okay? It might be minus infinity, but it exists, okay? So this inf I'm going to call I epsilon. Then this inf converges, so and let's say, no, I'm going to do it like that, and let's say that there exists a U epsilon which is epsilon closed, such that since it's an inf, f epsilon of U epsilon minus L of U epsilon is less than the inf plus epsilon. So maybe here I'll assume that the inf are, I haven't thought about it until I talked about it, but let's say I assume that the inf are uniformly bounded from away from infinity, so that it makes sense. Then the result is the following. Provided that U epsilon in the norm X is bounded uniformly in epsilon, then u epsilon converges to a u, or a subsequence actually of u epsilon, a subsequence of u epsilon converges to a u in X, and u is a minimizer for f of v minus LV. More specifically, so what does that mean? That means, in particular, that if this problem for a fixed epsilon has a minimizer, and if the sequence of minimizer is bounded uniformly in epsilon, which is usually a property of the, which people refer to as coercivity of the functional, then the limit functional is minimized at the limit of the minimizers of the minimizer for epsilon. So in order to compute the minimizer of this problem, all I have to do is to find a sequence of approximating problems with which gamma converges in some topology which I'll have to specify to that problem. And then if I can minimize or even infimize, approximately minimize each element in that sequence of approximating functional, I will construct a sequence of near minimizers which will converge to a minimizer of this. That's the property of gamma convergence. So here is the issue is, how do I find a sequence of functional which gamma converges and in which sense to this functional. And the result in the case, in the setting of image segmentation, which has to be slightly modified here, is a result of Ambrosio and Tortorelli. So it's a result which dates back to the beginning of the 90s. Tortorelli. And it says the following, and I'll write it just to be, you can write it in any context, but for now, for what concerns us today, I'll write it in the case where psi of f is 1/2 of f squared, or maybe you can put some coefficients if you want. So it says the following. It says, consider the functional f epsilon, which depends on two variables, u and v, and which is defined in the following way. Integral over omega, and then I'll modify it somewhere. I'm giving you the version for image segmentation, and I'm going to modify it slightly. V squared plus eta epsilon 1/2 grad u squared plus epsilon grad v squared plus 1 minus v, or v, 1 minus v squared over epsilon, or maybe 4 epsilon, I never know. There's a 4 somewhere, yes. Okay. So this functional, so it's a two-field functional. Gamma converges. So you have two fields. So each of the fields you have to, there's a topology. So it has to be on a product space. So we'll put it in L1 cross L1 of omega. Or L2, it doesn't matter. 2, so this, the functional here, I'll call it f of, so psi, well, I'll write it, to f of u, which is equal to 1/2 of grad u squared plus k, maybe there was a k here, k h1 of SU if V is identically 1 and plus infinity otherwise. What does that mean? Okay. So first of all, it's not exact. What I wrote, I have to slightly alter it, but in principle, it's exact. So let's try and understand what it means first. Okay. Yes. So hold on. I have to specify a lot of things. So epsilon is a small parameter which goes to 0. Eta epsilon, I haven't told you what it is. So eta epsilon here must be something which is positive but small with respect to epsilon. When I write small like this, I mean that it goes faster to 0 than epsilon. So eta epsilon over epsilon goes to 0 as epsilon goes to 0. Okay. Now, I'm going to still modify it somewhat, but let's, because here you see you don't see the boundary conditions, and there are some things that are a little bit weird if you think about them. But let me just give you the intuitive one, tell you that it's not impossible that it be the case. Look at this guy here. So this guy is epsilon grad v squared plus 1 minus v squared over 4 epsilon. Imagine that you minimize this. So you have a u epsilon and a v epsilon. So clearly this functional is not identically plus infinity. I take u equals v equals 0. I get a value which is 1 over 4 epsilon. Or I take better. U equals 0, V equals 1, and I get 0 as value. Something like that. Yeah. So clearly, this functional is not identically plus infinity. I'll tell you why it's quite obvious that you can minimize this functional. There's a minimizer, U epsilon, V epsilon. Take this minimizer. It satisfies epsilon grad v epsilon squared plus 1 minus v epsilon over 4 epsilon squared, finite, integrated. Okay? So what happens? As epsilon goes to, and that value is independent, that bound is independent of epsilon, for example, that bound is 0. 0 is a little bit strange, but yeah, maybe because I have no boundary conditions here. So no. Yeah, because here, yeah, that's normal. Because in this, you see, if I was to minimize this without putting either a second right-hand side or a boundary condition, the minimizer is clear. What is a minimizer? I'm summing two terms. The minimizer is u equals 0, v equals 1. Period. So in general, I should add something to this, and I'm going to add something. But in any case, that's besides the point. The point is that this bound, so for a minimizer v epsilon, this guy will be less than some constant. As epsilon goes to 0, that means that 1 minus v epsilon squared over 4 epsilon, maybe I'm not writing enough and talking too much. So if the integral over 1 minus v epsilon squared over 4 epsilon is less than some constant, which is independent of epsilon, what does v epsilon go to as epsilon go to 0? 1, identically. Okay? 1 identically. So it is clear that the limit of v epsilon is essentially 1. Okay? So that's the first thing. Okay. One thing I forgot to say about gamma convergence is that the gamma convergence result, well, I said it here. You see, that gamma convergence doesn't see the linear terms. It's impervious. Gamma convergence is impervious to the addition of a linear term, of a linear functional which is continuous. So you could add a linear term here. Okay. So this is not quite what we want because okay. This is not quite what we want. Why? Because first, we don't have any boundary conditions, and that's it. Essentially because we don't have any boundary conditions. So we have to adapt it to the fact that there are boundary conditions. As I said, the right way to look at the boundary conditions is to impose the boundary condition as a value of your fields outside omega bar. So here what you do is the following. In order to make it work in our context, you do the following. You take omega and you put it in, let's say, a bigger box on which you're going to do your computations. On that bigger box, you put U, or U equals G0, if we're at the first time, on that bigger box. So U equals G0 on the box. So that box is B on, or omega tilde, on omega tilde minus omega bar. And this term here, which is here, so I put it on omega tilde. But that term I only compute on omega because I don't want to add, otherwise I would be adding essentially a constant. So I only compute that term on omega, but I compute that term on omega tilde. So why is there an eta epsilon here? Why is there an eta epsilon here? Because if you don't have an eta epsilon, when V is 0, this could be degenerate. By putting a small eta epsilon, you are making sure that for a fixed epsilon, the coefficient in the term of grad U square is always positive. Furthermore, if you take this functional, you're trying to minimize it, you can assume that V is between 0 and 1. Why is that? So let's see why. Let's say V is not between 0 and 1, and you truncate V. So let's say V goes past below 0 or past 1 or both. Truncate V to the value 0 and 1 when it is outside 0, 1. Leaving the U the same. That term will decrease because it's a square. That term will decrease, okay? Because either V was smaller than 0, and by cutting it back to 0, you decrease that, or V was greater than 1, and by putting it at 1, you make it 0. What about that term? That term will also decrease. Why? Because of the following result, which is a very simple result. That if you have a function V, which is in H1 of omega, and if you truncate V, so you take, so I call Tk the function, which is 0, which is like this, whose graph is like this. K. So it's a function which has slope 1 between 0, T1 I should call it, because that's all I need here. T1. So that's 1, 1. this function, which is 0 here, goes to 1 with a slope 1 and is 1 here, is such that T1v is also in H1 of omega, and that its gradient of T1v is indeed T prime 1 of v grad v, the derivative of v grad v. Okay. So it's essentially saying that the gradient of T1 of v is the gradient of v as long as v is between here and there, and then it's 0. Okay? So that's what I'm using here. I'm truncating v between 0 and 1, and this term will decrease. What else do I want to say about this functional? Not very much more than that. Yes, I want to say why for a fixed epsilon this has a minimum. So in the notes, clearly I won't do that today. I mean, in view of the fact I only have a half hour. But in the notes, I give you some reasons to, I give you nearly the complete proof of the gamma convergence. So for those who are interested in the math, it's there, modulo a few issues, but I'm not going to do it here. I don't have the time. I'd rather show you. I think you're also tired, so I want to show you a few computations. So why does this have a minimum? That's very easy. So maybe we'll do that. So first of all, yes, I should add here that I'm imposing U equals G0 outside omega bar. Or omega, it doesn't matter here. Okay, so what does he have a minimum? Well, certainly take G0, I'm in this situation. I have omega, and I have omega tilde like this. And here I have U equals G0. So certainly I can take a test function V equals 1 and U equals G0. I get a value. Since 1 here, this is 0. 1 here, this is epsilon, eta epsilon grad G squared. So certainly the inf of f of epsilon of uv is less than a function 1/2 of integral over eta epsilon of gradient G0 squared, which is certainly less because eta epsilon is of the order of, is something which is going to give you a constant here. Okay. So now I take a minimizing sequence of this. So I take a un and a vn such that f epsilon of un vn, so this inf I'm going to call I epsilon, goes to I epsilon, decreases to I epsilon with n. So epsilon is fixed and n goes to infinity. And then I look at the properties of un epsilon, of un, sorry, and vn. So obviously, because of this term, grad un epsilon, grad un is bounded in L2. And because of this, grad Vn is bounded in L2. And on top of that, I saw that I might as well take Vn between 0 and 1. And from this, plus the fact that un is G0 outside omega bar, I get that un and Vn are both bounded in H1 of omega. So if you know that, it's obvious. If you don't worry about it. And so converge weakly to a U and Vn to a V in H1. So it's in the strong topology of L2, but the weak topology of H1. And then you just pass to the limit in each of the terms by elementary properties of the L2 norm, which is lower semi-continuous with respect to weak convergence. So once again, this is just for those of you who have a little bit of a math bend. Okay? So then you get that UV is a minimizer. So I call it U epsilon, and V epsilon is a minimizer. However, notice the following thing, and that's very important for numerics. This functional here is certainly convex in U for a given V. The dependence is just grad U squared. It's a convex functional. It's convex in V for a given U. Why? This term is convex. 1 minus V squared is convex. This term is convex, it's V squared. And this term is convex. So it's convex in U and it's convex in V. But it is not convex in UV. Okay? All right? It's not enough to be separately convex in R2 and to be convex. Because to be convex is the Hessian matrix is convex. To be separately convex it means it's in each direction. So if you write, it's a completely different condition on the Hessian matrix. Okay. So the facts. So now what do you do numerically? Numerically, you want to minimize this in UV. The problem is, how do you minimize a non-convex function? And if there are no algorithms that I know of that ensure that you converge, that when you do numerics, you can converge to a minimizer of a non-convex function. If you have a convex function, you can use whatever algorithm you want, steepest descent, whatever. You can use all those big words. I mean, we all use big words in our field, but the big words in numerical analysis can be very scary, conjugate gradient method and things like that. But if it's non-convex, whatever you do, you will not show that you converge to a global minimizer. And so what do you do? So what do we do to minimize this thing? Well, we don't. So, or maybe one more thing I should say, because I'm in Italy, so I should say that. There's a very famous problem in physics and in geometry, and which is on par, if you want, with Euler, which is a problem of minimal surfaces. Okay. So the problem is for example, on a given domain, omega, I give myself a set A, a subset A of omega, and I want to find the subset A of omega which has volume 1/2 of the volume of omega and minimal perimeter. And there's a famous result by Modica and Mortola. Which says that this problem is approximated by gamma convergence, in the sense of gamma convergence, by the following problem. I'm not sure about the 4 here. With the constraint that the integral of V should be 1/2, probably. That as epsilon goes to 0, V goes to the characteristic function of that set. And that this functional goes to the perimeter of that set. Okay. This is very close to that. It's not quite the same. And I'm saying that for people who do computations. There is a huge literature in fracture mechanics, which is very fashionable these days, and which you will find you will find a lot of those articles in Physical Review Letter PhysRev B, which is a very good journal, where instead of this functional, where they do what. Yeah, I'll comment on this, I'm sorry. Where instead of this, they put that. Don't do that. Never do that. Because this generates sets of finite perimeter. So this generates sets that have no choice but to be closed, to have a boundary which is closed. It's either closed because it's going to go to the boundary, or it's closed because it's going to form this. A crack is not the boundary of a set which has a finite perimeter, because otherwise you would never have a crack that stops somewhere. It would have to either go to the boundary or loop upon itself, which is not what we think cracks are. That functional, for reasons which we could discuss, but not now, only generates sets with perimeter sets of finite perimeters. So it cannot be the right function to use here. So which brings me to another comment about those things, which is that, so now it's a comment for people who are more used to mechanics. This thing here looks very much like what people call a damage gradient model. You can think of V as a damage variable. So because in effect what it does is it makes V, so I wasn't very, maybe I should have been a little bit clearer here. So V goes to 1 almost everywhere. The crack, so V goes to 1, but V is just a function which is defined almost everywhere. The crack will be essentially the location of where V is not 1. But of course that doesn't mean anything because you can change V on a set of measure 0 and you don't change the limit. So you have to be careful. So in principle, in your head, you can think, I do this, I get a U epsilon, a V epsilon, but the set of where V epsilon goes not to 1 is my crack. But that means nothing because the convergences are not so strong that you can say that V epsilon converges pointwise. However, there's a more refined result, which is that when you evaluate this at V epsilon, this thing here, without the integral, goes to the measure length restricted to the crack. In particular, this thing goes in length to the crack length. Okay? So okay. So that's what I wanted to say. No, I had started something about, yeah. So you could see this as a gradient damage model. Why? Because V would be, so you have the crack, think of V epsilon as something which is essentially, which is going to be 0 in a neighborhood of the crack you're looking for, and essentially 1 elsewhere. So this looks very much like what people would call process zone. Epsilon would be essentially the size of that process zone. And so what you would say is that you have a damage variable, which is V, which is going to localize around the crack. And it's like a gradient model, not at all the same kind of second gradient that Francesco is introducing. You know, this time it's an internal variable, V, and you're associating some if you want, some dissipation, which depends also on the gradient of V. So those are models, gradient damage models. You can interpret this if you want like that, but you shouldn't pay too much attention to the physical meaning of that, because this is just one way to approximate this functional. There are many other ways you can approximate the M&MoCS functional, which don't look at all like damage gradient models. So if you think, it depends on what you want. If you believe in damage and that fracture is some limited case of damage, of some damage mechanism, then probably this is a good model, and it involves, you need to introduce gradients, okay, with a small length for your a small process zone, if you want. But if you think that fracture is the overarching model and that you're just trying to approximate it for numerical reasons, then don't pay too much attention to the mechanics of this. So here it depends on your viewpoint. That's not, I tend to think that this is more fundamental than that, but maybe I'm wrong. Maybe damage is more fundamental. Okay, so how are you going to minimize this here? You're going to minimize this. You're not going to minimize it because we don't know how to minimize it, but you're going to do it by alternate minimization. So you fix epsilon. You start with your first guess for UV, a reasonable guess if you can, and then you minimize in U with that V. Then you take the resulting result, you minimize in V for that U, and you keep on doing this, and you alternate. What you're going to do when you do that clearly is you're going to have, so it's epsilon is fixed, you're doing this for a fixed epsilon, you're trying to find U epsilon and V epsilon. What you're doing when you're doing this is certainly a numerical method which decreases the energy at each iteration. But what you converge to is not clearly even a local minimum. The only thing you can prove is that it is clearly a stationary point of this functional, that it satisfies the Euler-Lagrange equation. But since it's not a convex functional, it's not the same as saying that it's been minimized in any way, shape, or form. I do not know of any algorithm, again, that allow you to minimize this. So now I think, I have 15 minutes. I'd like to show you a couple of things. And hopefully I'll finish a little bit early so that you can relax. Yeah, so I've shown you how to minimize this at a given time. Of course, you have to combine this with a time evolution. And in particular, you have to combine this with the irreversibility. So there's one thing which which is, so essentially, so when am I going to define, so what am I going to show you numerically? Numerically, I'm going to show you computations not on this, but on that. I'm going to say I'm choosing epsilon small. What does it mean? That's always a difficulty. What does small mean? I'm going to show you not probably U epsilon, V epsilon, but some result of this alternate minimization. When do you stop the alternate minimization? Essentially when the energy stops decreasing for a little while. But there's no guarantee that 200 years later, the energy would not start decreasing again. So you could be running this computation for since the times of those people over there, and still be minimizing. Still be decreasing. So you stop. There's no convergence result or anything. It's completely heuristic. There is a description of an algorithm which helps for local or global minimization in the notes, which I won't talk about, which is called backtracking. Yeah, and then so then you've minimized at a given step. So you've gotten what I'll show you is, let's say, the set of points where V epsilon is less than 10 to the minus 2. And I'll say that's my crack. Why 10 to the minus 2? So that I get something which is not too, which is fairly thin. If you want it, you could do it at 10 to the minus 4 or whatever. Okay. There's no uniqueness here either, although for some obscure reason, you can run this in all the problems that we've run with different initialization. You always end up with the same thing. So maybe there's a uniqueness principle but maybe it's due to the numerical technique, okay? Or maybe there's a uniqueness which we don't know, which we don't understand. Yes, so, okay, and then how do you advance? Well, you'll advance by deciding that once V epsilon was 10 to the minus 2 at a given time step, you put it to 0, and it'll stay 0 for all future times. So you essentially increase the area where V epsilon is 0. So that way you enforce irreversibility. All right. So colors are going to be level sets of, or sub-level sets of V epsilon. So let me show you, so let me maybe come back to this computation here now. File, open with, so I'm coming back to this computation. So you see, so what's happening? Oh no, I'm coming back to it, but it's not showing on the.
You have to wait.
Yeah, I'll wait. So you have this elastic. So it's an elastic plate, which is clamped here to a rigid shaft. It's 2D. It's a 2D computation. So I never know if it corresponds to plane strain or plane stress. Plane stress, probably. And then you're pulling on this over there. And at the beginning, it's completely elastic. And then you're pulling. And so what you see here, those variations in blue are level sets of your function V epsilon. And then suddenly, at a given time, so it's really at a given time.
So this V is a kind of auxiliary
variable. Right.
But, you know, you would give the interpretation in terms of damage factor.
Yeah, it would be like a damage variable.
But how is it possible that V over the crack in the previous frame?
Yeah. Jumps.
Becomes hell, and then here becomes again dark blue. So where is damage is damage. The previous frame. Over the crack is hell.
Is what?
Hell, hell blue. I mean.
Light blue.
Light blue. Yes.
Yeah. So.
The next, then the crack is.
Because.
It's not damage.
No. That's because I said something. That's a question of how you enforce the irreversibility. That's a very good question. Good. Impressive. I don't enforce the irreversibility by saying that V epsilon should decrease everywhere. I enforce the irreversibility. You could do it like this, but it would be computationally not, expensive. I enforce it by saying from one time step to the next, I forget what V epsilon was previously, except when V epsilon was less, where V epsilon was less than 10 to the minus 2, where I put it to be 0. Okay? So that's why that light blue here has disappeared. Very good.
Once it becomes 0, it remains
0. But when it was where it was 1/2, it can go back to 1, which is not very good point, which is not what you would expect. And actually, because there's a proof, you can do an evolution for this damaging in the same spirit as we did. And when you do the proof that this evolution converges to the evolution for fracture, you do need to impose what you're saying. So we are cheating here. Okay.
ISM, you have heard this name.
Yes, of course.
Claims that this V is the gradient of U, or it gives it in terms of constitutive equations.
I don't think so, because it should be an internal variable, I think. I mean, yeah. Oh, you didn't have a question? No. Okay, so what I think is more, but maybe that doesn't shock you, but what I think is more is fascinating is no crack. Okay. No crack. That's a brutal initiation.
But do you have changed a time step?
No.
I mean,
uniform. Oh, okay. Finite element. Uniform. No mesh refinement. Against mesh refinement. Bad idea, mesh refinement. Bad idea. Because mesh refinements drives artificially the crack where it maybe shouldn't go. With mesh refinement, you tend to refine in a place where you already have the crack. And you may miss.
You introduce artificial length scales.
Yes, exactly. You introduce a length scale. You should do a first computation without mesh refinement and then redo the computation, refining the mesh where you found the crack. Except, I'll show you, okay, so now
but I was talking about time step.
Yeah, time steps are uniform.
Maybe.
Not in, okay, there are 2 time steps, okay. There are 2 time steps. You have the time of the evolution and you have the time of the iteration. How many iterations you need for this, I don't remember. This is 2D, it's not so hard. You can do this on your PC.
This sudden appearance of the crack.
That's in 1 time step.
Okay, so maybe if you refine...
1 time step.
Always?
1 time step. It's brutal. It's really brutal. Okay, and then it's progressive, you see. It goes progressively and symmetric. But then at some point, and this is typical global minimization, the crack here knows that there's a boundary for some obscure reason, because God endowed the crack with X-ray vision to see the boundary, and it knows there's a boundary, and it knows if it cuts right to the boundary, it's going to decrease the global energy of the material. Of course, it's nonsensical. But it's not so nonsensical, because what is happening really in this thing probably, by the way, so you see it cuts, and then it goes and it does the same thing. Now, this is completely asymmetric. Why it cuts on the left rather than the right? That's undecidable. The computations which were done by Blaise Bourdin, he's very cautious, for those of you who like computations. So he's using a regular mesh, but he's very cautious not to favor any direction. So he uses Delaunay, I think is the right term, mesh, so that there's no preferred direction. Okay? So why it goes to the right rather than to the left? Don't know. But in other numerical experiments, it would go to the left rather than to the right. But it goes one way and not the other. That's like buckling. It buckles. Where it buckles, you don't. Which direction it buckles, you don't know. But it buckles in one direction rather than the other. And then it closes, and it cuts. Now it might be. So now this is science fiction. Huh? Now it might be that actually this is completely, first of all, it's what you observe for this problem qualitatively. And second, it might be that what you're doing here with global minimization is you're mimicking pretty well what happens if you introduce dynamics. So here, something, in those two cases, here, when you go brutal, and then when you go here, there's some dynamics that are happening, fast dynamics, that we don't know how to capture. Our model is quasi-static. Somehow, this is probably some reasonable, maybe, variation, some reasonable variation of dynamics. So let me show you some more interesting computations. So here is one. So this is an interesting thing. So you have a material here which is unbreakable. It's a 3D computation. You have a material which is unbreakable. It's a shaft, a cylindrical shaft of circular cross-section, which is surrounded by an elastic, brittle material, which is perfectly bonded here. Okay, but which can break. The middle cannot break. It can stretch, but it cannot break. And then you come and you pull like this. What do you think will happen? So, of course, you've all probably looked at my notes, so you know what will happen. But what is happening is the following. So here is a 3D computation. So what is shown here is the crack. What is shown here is V1 minus V in the evolution. So it's the so here is what happened. It first deforms elastically, suddenly. Okay. So let me reduce this. So you see it first deforms elastically, and then a first crack appears. Or no, or it doesn't want to appear. Up. No, that was before. Yeah, it appeared before, but no, it's probably because I don't know how to stop the movie. I don't have the command of the movie. I don't know why. I cannot see the command for the movie, but so you see it appears and then it starts cracking periodically like this. And you so something which is important. Let me stop the movie here. I don't know if you can see that, but since it's bounded here, over there, there is bending of the core. The core is unbreakable, but it bends. It's bending because of the difference between elasticities of the core and the bonding. So you have the core does this, and then you have this crack. And this is something which is observed. Exactly, this kind of transverse cracking is observed. So once again, it's qualitative. Unfortunately, yeah, I'll take 2 more minutes and then I'll stop. Unfortunately, it is extremely difficult, and I don't blame anyone for that situation, but it is extremely difficult to get anyone to conduct an experiment for you in this matter. Why? Because if you're an experimentalist in a university, be it in Italy or in the US, why would you work on some other person's theory for a problem which is just quasi-static fracture? If you're an experimentalist in fracture, you want to do high-impact dynamics of bullets against titanium plates, because that's what is going to bring you money, and I don't blame them, and fame and recognition. And so nobody wants to do experiments.
Times when people
Yeah.
in the Academy of Science.
Yeah. But right now, for an experimentalist, there's no incentive to work on this. So the only thing we can do, and there are very few, if you look in the literature, I mean, we could look harder, but there are very few places where you can find a complete set of data. There's one area, and I'll finish with this, there's one area where you can, and this is...
You're guessing the crack energy, right?
Yeah, but you need everything. You need to know what the fracture toughness is. You need to know you need to know a lot of things that are not available in the literature. So a long story. Okay, so here is, and I'll finish with this. I'm sorry, can I take 5 minutes of your time? Just to show you pictures, so it's kind of, so this is an experiment which falls within the purview of, it's not complete elasticity, it's temperature, but the temperature field is essentially given. So it's called diffusive cooling. All the computations are by Blaise Bourdin, and if you're interested in seeing a zoology of images, you should go to his website, which is at math.lsu.edu. He spent 6 years developing code. This is like, in order to do those kind of computation, not the ones I'm showing you now, but the next ones, you need to use parallel computing. So he has 128 processors running in parallel, and it takes a few days. So here is a glass slab which is heated up, you can read it, and lowered against dry ice. And what's happening is what is known in physics as the parking phenomenon. So your glass is first no cracks. And what happens is that there are cracks, so you take your glass slab, you put it on ice, and cracks start, the glass breaks, and cracks start propagating for the bottom part of the glass, but in a periodic way like this, but they park. 1 out of 2 parks. That means they stop, and the rest keeps on going. That's called the parking phenomenon. And it's a weird thing. Completely no theory can account for this that I know of. You can, okay. So anyway, here is our computation, this time with the real data. Huh? Okay, so we do, for reasons which we cannot explain. So it's a numerics, but we have no...
You have the equation.
No, we don't know how to prove this.
You are using equations.
No, we're using numerics.
Numerics based on equations.
Yeah, but that doesn't tell you that we're computing the right thing. For example, why is it that it's a periodic distribution of cracks? Why is it that some stop and others don't stop?
You have found by chance an action which produces your effect.
That's right. That's all. If we are computing what we say we are computing, which is not clear to me. No, I don't rely on me. I don't know. As you see, so now I'll finish, and that'll be my last one. I'll finish. Oh, okay. There's a zoology. There's an experiment which, in the solid state physics or condensed matter or whatever physics is really an important experiment. It's UCSano. So what they do is they take a plate and they dip it, a plate of whatever, so I don't know what this material is, I don't remember, and they dip it in a cool bath. And then so let's say the plate is at ambient temperature, and you dip it into a hydrogen bath what is it? Azote? I don't know. Yeah. What is it called in English? I don't remember. Nitrogen. Yeah, bath. And so you see that depending on the speed at which you dip it, and the speed at which, and the gradient of temperature between the air and the bath, you get completely different fracture patterns. And here is, so with the same data, this is the evolution that we get numerically. So once again, it's qualitative, so we haven't compared the amplitude or the frequencies, but and there's a zoology and we find the same zoology. So depending on the speed, sometimes it goes straight, sometimes it goes like this, that's the one from before. Sometimes there are many cracks that appear. And there's one regime that we found that has not been observed experimentally, and I submit it to you because it's an interesting, fun regime. But we haven't found any data for that range of parameters. Okay? So finally, I don't know if you've seen this, but I have. You go to, so I haven't seen it in Ireland, but you go to, so apparently in Northern Ireland, you have what's called the Giant's Causeway. And you see those structures which are kind of pentagonal, but you cannot pave the plane with pentagons, so you have to introduce some hexagons. So I don't know if you see some pentagonal structures. I mean, okay, it's nature, huh? And some hexagonal structure. You see the same thing in a place where I've been, which is the Salar de Uyuni in Bolivia, which is one of the most fantastic places on earth, where you see, because this is about 100 kilometers in diameter, and this is salt. And you see these patterns here like that. Okay, so hexagons and pentagons, a lot of pentagons. I mean, I haven't counted, but there's a greater ratio of pentagon to hexagons. And so this is thought to be a result of exactly the same kind of diffusing cooling that I had before. This is probably due to water seepage, but formally, when you write the equation, it's the same thing as the first experiment that I had before. And here is what we observe. So this is a nice 3D computation by Bourdin, where he did exactly the same kind of diffusive cooling that I showed you before, but in 3D. And that's the cracking pattern that he gets. That's a cross-section. And I'll show you the movie of the evolution. So you see that the evolution of the crack in 3D. Okay? And that's a cross-section of that at a given time. This is a heavy computation. Okay? So whatever. It just tells you that this method at least can generate this kind of topology numerically. Whether or not it has anything to do with nature and with the way cracks propagate, it's up to you to judge. Thank you for your attention. I'm sorry I went over by 10 minutes.
You seem to know better, so why don't you still say what?
Okay, so
I'm afraid to be too negative, so I will try to.
okay, so I should just
Go ahead.
no, just maybe it's necessary to compare, just to plot level sets of stresses and to see if your
fractures propagate in the direction of orthogonal or tangential to the, just to compare two methods.
So I'm not going to answer this, but I'm going to tell you something which is for those of you who have studied fracture, you've noticed a conspicuous absence of an important witness in the courtroom, which is stress intensity factors. So if you take a classical course in fracture, the Griffith theory takes 1 hour, 1 week, and the rest of the semester is dedicated to the computation of stress intensity factors. We don't compute stress intensity factors. We don't care about stress intensity. Of course, here, I'm not saying they don't exist. So what Sergei is alluding to is the fact that in linear elasticity, in 2D isotropic, it is said that, and probably true, although unfortunately Professor Berdichev is not here because he jumped again, but it's probably true that the singularity of the crack tip is in square root of R. So that means the stresses blow up like 1 over square root of R when R is a distance to the crack tip. I have yet to find a proof of this according to modern mathematical standards, except in one situation, which is isotropic, homogeneous. So the idea that Sergei is alluding to is that essentially you kind of think that the crack is going to propagate in a direction which corresponds to where the stresses, normal stresses are max. The stresses which are normal to the crack that would develop are maximum. So this is a story which is related to what is called kinky. And kinky is a study of what happens when you have a crack and when it suddenly changes direction. And there are several methods to do kinking in fracture mechanics. The problem is that in order to do that, you have to import something. Some people are importing a criterion. So here's the way they compute the crack path. They say each time the crack should be such that it is always going to extend in mode 1. Mode 1 means it's only going to be, it's going to go in a direction so that the lips of the crack are only in traction computation. So with that you can do computations, and some computations are done. Other people say no, the crack should propagate in a direction where the energy release rate is maximum. So you explore all possible directions, you compute the energy release rate, which is a derivative of the energy with respect to in one direction, and you go in the direction which has maximal energy release rate. There's a little unfortunate thing, which is that those two directions, usually the one where the cracks are in pure traction, and those where the maximal and the energy release rate is maximal, are not the same in theory. Now, if you say that to somebody who does fracture mechanics, they kill you. Why? Because they think the difference is 0.1 degree or 0.2 degree in angle. Okay, there's a difference. So from a theoretical standpoint, you're not doing this. So people do that. There are other methods as well. Okay, so whatever, it's a game where there's no blueprint of. Unfortunately, the fracture community is not mature enough, in my opinion, to decide here is a problem, and let the best person win. As long as we don't have that, it's just my word against your word. You had a question. Yeah, I'm sorry. He had a question first.
Okay. Well, first of all, thank you very much for the very nice presentation. That it was really very, very beautiful. And I have some, just a question for you. It's the result that you produce, beautiful results about the periodic arising of cracks. it is something that reminds me very much it's a class of phenomena like, I don't know if you know the Bernard convection.
Yeah, well, I know a little bit.
Bernard convection. So it is something in which you have just a fluid, then you have just a jump in temperature. Then if you set this temperature jump and you increase that, you have initially nothing that is... then you have periodic structures, and then you have a route to chaos, in the sense that every time the pattern is disappeared. So I don't know if this kind of problem that you are showing can belong to the same class of phenomena, the case in which you have periodic fractures. So maybe that acting on some non-dimensional parameters in your problem, you can pass through a periodic pattern and then to chaos in the deformation of the cracks. This is the question.
I have never thought of that, so that's possible. However, am I mistaken in saying that in Bernard convection the only dissipation is viscosity? Right? So it's a different kind of... So in that respect it's a bit different because here it is fundamental that it be rate independent. And somehow in Bernard convection it's rate dependent, right? The velocity plays a role. But I'd like to hear more about it. I have no...
Thank you. But here you are doing global minimization because
I'm trying to do global.
Yes, because you have the mathematical tools.
Yes.
But usually in nature, everything evolves through local minima.
It's a very good question. But that's the wonders of numerics. Actually, as I told you, as I told you fairly detailed, I'm not sure that I'm computing global minima.
Yes, but
actually, I'm not even sure I'm computing local minima, but I'm sure I'm computing station minima. So it might be that what I'm computing numerically is actually closer to what nature will.
But if you don't use the
tracking,
tracking,
yeah,
yes,
it might be so that it's better from from a mechanical standpoint. But the problem is you don't have the math behind it to justify what you're doing from numericals. So it's a trade-off, but you're right. Very good. Maybe break now.